Hello learners, I am Dr. An Assistant Professor of Chemistry from the Ganpat Pasagar College of Education, Goa. I welcome you all to this Chemistry MCQ Solver course. In today's session, we are going to see some commonly asked MCQs based on thermodynamics. Let us look at the first problem. The heat of formation of methane at 27 degrees C is minus 19.3 kilocalories. When the measurements are made at constant pressure, what will be the heat of formation at constant volume? The options are minus 13.3, 4.76, minus 3.12 and 14.85 kilocalories. This problem is based on the heat of formation. Applying the relation delta H equals to delta U plus nRT, wherein the delta H is the heat of the reaction at constant pressure, whereas delta U is the heat of the reaction at constant volume. Given that the value of delta H equals to minus 19.3 kilocalories for the reaction of C plus 2H2 giving CH4, number of moles of the gaseous reactants given are equal to 2 and the number of moles of the gaseous products equals to 1. Thus, delta N becomes 1 minus 2, which is equal to minus 1. Substituting this value in equation 1 above, we get a value of delta U as equal to minus 19,300 minus 5,961 calories. Thus, delta U comes to minus 13339 calories or minus 13.339 kilocalories. Thus, option A is the correct answer. Let us look at the next problem. Calculate the pressure volume work performed by the system during reversible isothermal expansion of 2 moles of an ideal gas from 2 liters to 10 liters at 20 degrees C. The options are 142.3, 7842.9, 6525.2 and 852.2 joules. This problem is based on the isothermal reversible expansion of the gas. Here we are given N equals to 2 moles, V1 equals to 2 liters, V2 equal to 10 liters, temperature will be 293 Kelvin, R is given as 8.314 joules per degree per mole. The maximum work done is given by the expression minus 2.303 nRT log of V2 upon V1. Substituting the given values, we get a final answer of 7842.9 joules. Thus, option B is the correct answer. Let us look at another problem. For a certain gas, Cp equals 8.58 joules, 2 moles of the gas are expanded adiabatically from an initial temperature of 20 degrees C to a final temperature of minus 45.4 degrees C. Calculate the work done in the above case. The options are minus 542.2, 896.2, 1521.5 and negative 3624.9 joules. This problem is based on the adiabatic reversible expansion of gas. Cp, that is the pressure capacity, is given a value of 8.58 joules. Cv, volume capacity, has a value of 8.58 minus 2, which comes to 6.58 joules. R is equal to Cp upon Cv. If we substitute the values of 8.58 and 6.58 in this expression, we get a value of R as 1.3. Other values given are N equals to 2 and the gas constant, that is R, which comes to 8.314 joules per Kelvin per mole. If we substitute this in the expression for work, which is W equals minus NR into T2 minus T1 divided by 1 minus gamma, we get a final answer as negative 3624.9 joules. Thus, option D is the correct answer. Let us see the next problem. Calculate the standard enthalpy of the reaction for the reaction CO2 gas plus H2 gas giving carbon monoxide plus water. Given that delta H naught F, that is the heat of formation for CO2, CO and water, are negative 393.5, negative 111.3 and negative 241.8 kilojoules per mole respectively. The options are 15.3, 90.5, 7.9 and 40.4 kilojoules. This problem is also based on the adiabatic reversible expansion of a gas. The delta H naught for the reaction, that is CO2 plus H2 giving CO plus water, is delta H naught equals to H naught of products minus H naught of reactants. If we substitute the given values, we get a final answer of 40.4 kilojoules. Thus, we can say that option D is the correct answer. Let us look at the next problem. What is the enthalpy change for the reaction hydrogen plus bromine giving 2 molecules of hydrogen bromide? Given that the bond energies of HH, HBr and HBr are 435, 192 and 364 kilojoules per mole respectively. The options are, let us look at the next problem. What is the enthalpy change for the reaction H2 plus bromine giving 2 molecules of hydrogen bromide? Given that the bond energies of HH, BrBr and HBr are 435, 192 and 364 kilojoules per mole respectively. The options are minus 101, 101, minus 61 and 61 kilojoules. This problem is based on calculating the bond energy. The standard enthalpy change for the reaction is given as summation of bond energies of the reactants minus the summation of the bond energies of the product. So if we substitute the bond energies for the reactant side, that is HH and BrBr, minus 2, that is the 2 molecules of HBr, so it will be 2 into the bond energies of HBr, and if we substitute the values, we get a final answer of negative 101 kilojoules. Thus, option A is the correct answer. Let us look at another problem. What is the amount of heat supplied to Carnot cycle working between 368 Kelvin and 288 Kelvin if the maximum work obtained is 895 joules? The options are 432, 7185, 4117 and 782 joules. This problem is based on the Carnot cycle, wherein the neta, that is the efficiency of the engine, is given as W divided by Q2, which can be expanded as T2 minus T1 upon T2. If we substitute the corresponding values, we get an expression for Q2 which is equal to 895 into 368 divided by 80. Solving this, we get a final answer of 4117 joules. Thus, option C is the correct answer. Let us see another problem. Calculate the molar entropy change of mixing 0.2 mole of oxygen and 0.6 moles of nitrogen at 25 degrees C, assuming that they are ideal gases. The options are 4.67, 2.52, 1.35 and 9.52 joules per Kelvin per mole. This problem is based on calculating the entropy of mixing of ideal gases. Given N1 equals 0.2 moles, N2 equals 0.6 moles, X1 equals 0.2 divided by 0.8, which comes to 0.25, and X2 comes to 0.75. Using the expression for delta S of mixing, which is equal to minus R into X1 ln X1 plus X2 ln X2, substituting the values of R, X1 and X2, we get the final answer as 4.678 joules per Kelvin per mole. Thus, option A is the correct answer. Let us see one last problem. What is the free energy change accompanying the compression of 1 mole of CO2 at 57 degrees C from 5 atmosphere to 50 atmosphere? Assume that CO2 behaves like an ideal gas. The options are 850.8, 1510.1, 352.3 and 2315.2 calories. This problem is based on calculating the free energy change. Given that N equals to 1 mole, temperature comes to 330 Kelvin, P1 equals to 5 atmosphere, P2 equals to 50 atmosphere, value of R is given as 1987 calories per degree per mole. Substituting this in the expression for delta G at constant T, which is equal to 2.303 nRT log of P2 upon P1. If we substitute the values of 2.303 into 1 into 1.987 into 303 into 50, that is P2, divided by 5, that is P1. We get the final answer of 1510.1 calories. Thus, option B is the correct answer. Thank you all for your kind attention.